Right. So today I'm going to be talking to you about the ingredients of mobile phones, probably something everyone has here and maybe are even watching this video, this talk on it. Yes, they're so, so common that this is what I found in my local Tesco's last night when I went to get some orange juice. You can buy oranges and mobile phones in any size shop now. They're just ubiquitous. But unlike oranges, they don't actually grow on trees. I don't know how many have really thought about what goes into them, but there's now, in researching this talk, I found there's at least 50, if not even 60 different chemical elements that go into making a mobile phone operative. In contrast, a higher, plant like an orange tree only has 17 different chemical elements. So, you know, a third of that. But a bit like oranges, the chemical elements that are in oranges do come from the ground. They're just made biologically incorporated into the fruit, whereas mobile phones use all that and more, iron, nickel, copper, that you find in oranges. And it's mankind that sort of reconfigure things into a useful devices. So that's really what I'm going to be talking about today. Like, how did we get here? So I'll be talking a little bit about the evolution of the phones. I am more a mineralogist than a technologist. So some of that information came from my colleagues in the science, history, and technology section. So, you know, the evolution of the phone and the ingredients of it, then why we have so many. I'll just do a little introduction to chemical elements and minerals and, you know, the different properties they have and why that's useful to put in a phone. Then I will talk about what elements and minerals are found where, what parts of the phones, and where they come from. And I've written here, problems, because, you know, when you need something that much, there's chances are there's going to be problems. So I'll be talking to you about, you know, conflict minerals and things like that. And finally, I should mention that all the pictures in here, other than the orange tree, which is came off Google, but is shareable, all the other pictures are of specimens that are in our museum, mostly on display. I've tried to take pictures of the specimens you'll find and display. Some of them are in the collection center, but at the end I have a little map of where you can find them. And if you are not in Scotland, then our online resource, which I did about 10 years ago, but is basically still mostly correct. So before we get started, you might be confused at the difference between chemical elements and minerals. Minerals are made of chemical elements that are organized in a repeatable structure that forms a crystal, basically. So on the left are a little model that's actually on display showing red balls and green balls. And the red balls are meant to be the chemical element represent the chemical element of sodium, and the green is of chloride. And sodium and chlorine together make the mineral on the right, which is halite or table salt. Underneath chemical elements, you can see the periodic table. I'm sorry, I have to show you this because this is so useful for this talk, but it's basically the table of all chemical elements that are known. There's 118 that have been discovered, but some of them have only been sort of synthesized, or they they decay so quickly they don't really count. There's only about 80 that are really stable that can be used in nature to make minerals. So you can imagine you get different configurations of those putting together, and we have to date nearly 6,000 minerals known. There's about 150 just added to the list every few months. And we predict that there's probably only about 9,000 different minerals on Earth. So there we are, chemical elements and minerals. So minerals can be made of one chemical element. We know those as native minerals, and silver is one, gold's another, platinum's one. There are many, many minerals that have two chemical elements, like the salt, the halite I mentioned, but other ones like fluorite or even quartz. You've probably heard of quartz. The most minerals have about 3 to 5 different chemical elements in them. I'll mention a couple here, and then some at the bottom can have even up to 12 different chemical elements, which is pretty amazing given that it's in a repeatable structure. The one on the right, eudialyte, is, I've had to wrap the chemical formula around twice, and that has rare earth minerals. I'll be talking about it later, so that will come up again. So how did we get here? This is a bit about the evolution of, well, phone technology, I guess. On display, we have a mock-up of the first patented phone done by Alexander Graham Bell in 1875. And this is it on the left. I don't know how it works, but I'm just going to talk to you about the ingredients of it. Yeah, there is an Australian expression, I know it is Australian anyway, that everything is either made from things you grow, and if you can't grow it, you have to dig it up. And this phone is a good example of how we use things that are grown, wood for the frame of the phone, and 3 metals which were dug up: iron, tin, and copper. Very common minerals. These were partly used because they've been known about for a long time because they have very simple chemistry, so they're easy to extract from the ground. So this just shows the chemical elements: copper, iron, tin, but the minerals that they come from is copper hematite, which is like iron oxide, and cassiterite. Back to our chemical periodic table. Here I'm shown in pink all the elements that have been known since antiquity. I mean, copper was known about from 7,000 BC. Most of these were known from thousands of BC, and it is because they were quite simple. That was, if you find copper in the ground, it's pretty clear it's a metal. Likewise with gold and silver. So that first phone from 1875 only used the, very well-known minerals. Oopsie. Moving forward to other phones, here are some ones from the 19th century and then the 20th century. Gradually, the wooden or grown frameworks started to be replaced with more other hydrocarbons, but hydrocarbons that come from petroleum projects. The metals that were used were started to be expanded. By 1937, we used all those metals that were known from antiquity, including lead and zinc, but we also added more metals to it. So nickel, aluminium, copper, but it's still only just a handful. You can see this cobalt and nickel were just the 2 added that were not, were fairly found or isolated, I should say, in the 18th century. So here we are today. This is a picture of a mobile phone with the periodic elements of every known element that I could find a reference to it in the literature. I should say there is nowhere that I can find a recipe for a mobile phone. There's nowhere that says these are all the metals you need to make an iPhone. I did find that there was a study where someone had broken down a mobile phone into its constituent parts, and you've had elements like palladium, which were in quite large amounts, but there was no mention anywhere where that was in the phone. So it's obviously this is industrial secret, so I'm doing my best to estimate. So I can find 54. I've read other references to up to 62 different chemical elements. Anyway, a huge amount, particularly when you compare it to what human bodies need, which is a fraction of the amount. It's pretty amazing what a human body on the right does with the elements on the left. Anyway, why do we need so many chemical elements and/or minerals? Back to the periodic table. Most of the periodic table has metals, and the way the elements are arranged is that lighter and smaller is in top left, and big, heavier and larger is on the bottom right. So metals basically conduct electricity. That's one of the things that they do, and just do it to different with different sizes. In yellow on the right are non-metals, which don't conduct electricity very well. And in between are semiconductors. And when it comes to mobile phones, semiconductors are really important because they basically conduct electricity sometimes and don't others. And that means they can work as a switch. And with a switch, you can do lots of different things. I found this table online, and it just shows you the periodic table, and the size of it shows the property. So at the bottom, excuse me, down here, I don't know whether you can see my cursor. Can you see my cursor? You can see the abundance. So there's a lot of silica and oxygen in the world, in the crust, but hardly anything else. The point is that these subtle differences all play a role and are being harnessed, whether it's density or temperature, boiling point, or thermal conductivity. These small differences make a really important difference when you're trying to make small things, basically. Putting these chemical elements together, minerals also have properties that are really useful. Well, you all know metals conduct electricity, and they're malleable. Gold is so soft you can't even make rings with it unless you mix it with another alloy. Well, that's true for all the metals. You know, you can, the military equipment uses alloys with tungsten in it because that's super hard. But yeah, so that's metals. Then we have ferromagnetic. That's really important because that's the magnetic properties, which you'll hear a lot about. And we have a natural magnet in the mineral world called magnetite, obviously. There's another one called escalite, I discovered, very rare mineral. Otherwise, the ones at the bottom are back to the semiconductors. Quartz is one of the most important ones. So these are the ones that can be, they have piezoelectric properties. What basically means that if you put an electric current through it, it changes shape, or if you change shape, it will run electric current. And that means that the currents are expressed, can go on and off, which is very important. And quartz, as you all know, is an incredibly common material. So now we know that all these chemical elements and minerals have different properties. Where are they used in mobile phones? This is the sort of exploded mobile phone, showing you the different parts of the phone that I will be talking about in the next section. One is the case. Then the glass screen is a really important part. We have aerials. I'm not going to be talking about that. Magnets are super important because they allow things to be switched on and off. Everything's being switched on and off. I'm not an engineer, but that's what it seems to be about. Vibration units, you know, when your phone rings and all that kind of thing, it's vibrating. Circuit boards, now that's, oh, what's happened there? Did I switch it? Sorry. Circuit boards, and then finally the battery that allows everything to run. So we'll start with phone cases. These are basically made of plastics with different elements, you know, carbon, hydrogen, oxygen, but then you have other elements in them just to make them harder or more flexible or fire resistant if you have boron in it. Or metals, obviously there's some metal parts. Can you read that okay? See it okay? Great. The touch screens I find are one of the most interesting things, because you just think of it as one piece of glass. It's not, it's 7 different layers. Screens have to do lots and lots of things. First of all, they have to be clear so you can see through it. Secondly, they have to be hard, really hard, so that they don't break. And they're made of a property called Gorilla Glass, which was actually found by accident, that has glass. Glass is mostly made out of quartz or silica sands, and that's silica plus oxygen. And Gorilla Glass has aluminium in it. And at first, aluminium was an accident, and it was just ended up dropping on the floor, and they discovered that this was an extremely hard material. So now glasses are usually made of a mixture, or tough glasses are made of a mixture of feldspar, that's the mineral on the bottom on the left, which gives aluminium to the glass, and quartz. But it doesn't only just have to be hard, it has to be protect all the electronics underneath the glass as well. So it has to be protective. And this is where rare earths, those minerals at the bottom of the periodic table, come in. They enable the glass to be protective of UV lights, but they're also used at the very, very bottom underneath the glass as liquid crystal displays. And all the different rare earth elements have slightly different colors, and that's where the colors are on the screen that you can see. Then, once we've got through glass, you're down to the circuit boards, and this is all the alloys, you know, that I was mentioning. We have, well, we even have gold. Gold is so malleable that it allows very, very thin strands to be made, as well as wolframite. The other issue is these things are working really hard, and so it generates heat. So you need to have metals that can get rid of the heat very easily as well. You might have felt sometimes your phone gets a bit hot. It's if it gets too hot, it will start to damage the structure. So finding things that alloys that can dissipate the heat is important. And the other thing is heat makes things expand and shrink, and you have to make sure that things expand and shrink at a more or less the same rate. You can't have the screen expanding and everything else not, because that will start to damage it. So that's where all the elements come into circuit boards. And wires and solders. So of lead is a solder, but was it bismuth, I think? Is that right? Yeah, bismuth is starting to replace lead, and gold's used as a solder. Microprocessors, accelerometers, and chips. I have to admit, I'm just writing this down verbatim. I don't understand what an all these microprocessors do in detail, but gallium is one of the important elements. I should say that quite a lot of these chemical elements don't form the structure of some minerals. Like we have sphalerite here in the bottom right, which is a zinc mineral. it happens to have it's sort of like polluted, if you like, with other elements, and gallium is one of the ones in there. So when you're trying to get zinc, you find gallium. It's just how you find it. Quartz microchips, I mentioned that they're piezoelectric or semiconductors, and they are a really important part of electronics. They've been used since the, I think, 1970s. Quartz was used originally, like quartz crystals, mostly from Virginia, I think it is, somewhere in the eastern states. And that's one of the reasons is that it's very common. It's really tough. It doesn't scratch easily. It's clear, and it doesn't expand and contract too much. Quartz crystals were cut in a certain way at right angles to the long axis of the quartz, and then they were etched. They made slabs and then were etched, and then the metals put in those etchings. Nowadays, we don't use natural quartz because there's too many contaminants and things like that. We tend to find pure quartz, grind it up, and then make synthetic minerals out of it. But the property of quartz is a very important part of mobile phones. This has no minerals in it, but there are two little parts of a phone which I thought were pretty cool, because never really realized how phones vibrated. But what happens is it's just like a washing machine. There's something that spins, and then they put a lump that's off center, like having, I don't know, trying to wash a duvet or something. It all ends up on one side of the washing machine, and the whole washing machine makes your whole house rattle. Well, that's done, but on a very micro, very small scale. And to have something that vibrates violently enough that you can feel it, even though it's teeny weeny, you need to use those very heavy elements called rare earths at the bottom. So they're very important for adding small, effective weights. And the same thing happens, how do you know your phone's, how does the phone know which way is up? You have little weights on little elastic plumb lines, and that will tell the phone which way the orientation is. So this is another job. So rare earths are used as weights, as well as colors, as well as ways of making glasses UV proof. Microphones and speakers. The real thing here is magnets. That's the other very, very important role that rare earths have in particular, is to make very small but very powerful magnets. And they're used all through phones. Finally, we've got to batteries. Batteries, you've probably heard lithium is an incredibly important part of batteries. There's lots of different kinds of batteries, and I'm not sure if every phone company uses the same kind of lithium battery, but lithium batteries need graphite as an cathode, sorry. So introducing the importance, and tantalum is another one important for batteries. So that gets me to the list of all the minerals that have elements that are found in different parts of the phone. Putting them together, you can see that that's a lot of minerals to try and find and process. And that's the next part of this talk, is really where these minerals come from. This, can you read it, this screen? Not great. This map shows the key sources of minerals and chemical elements from around the world. And there's a couple of, see? Do you know, I think I'm playing it in the wrong kind, because you can't see the animations in this. Because you can see UK has a ring around it. Great. So the takeaways from this map are, firstly, there's not much from the UK. Secondly, there's quite a lot from places like China in particular, and DRC, that's a Democratic Republic of Congo. And this has some problems, as we're discovering. And I thought I would focus on three different, the supply chain related to three different minerals. One of them is tantalum. The next one is cobalt, and then obviously rare earths, which I've talked about quite a bit. We'll start with tantalum. Tantalum comes a lot, or at least it used to come a lot, from the Eastern Democratic Republic of Congo. And in the early 2000s, this there was a lot, and probably still is, of conflict between Rwanda and Eastern Congo. And it was discovered that the military were benefiting a lot from the mines. They funded 75% of the armed forces in that area, and they were getting massive profits. And obviously, as a result, there were a lot of deaths due to this, the economics of selling tantalum. They also mined tungsten and tin there, and although in terms of global importance, it wasn't so much from the Congo, it still helped to fund conflict. So in 2010, President Obama signed something called the Dodd-Frank Consumer Protection Act into law, and that defines 4 minerals known as 3TG, so tantalum, tungsten, tin, and gold, as potentially being sourced from conflict zones, and so that public companies need to make sure that they are doing due diligence and they're getting their mineral supplies not from these areas. This has been followed in 2017 in Europe and expanded to now it's 28 different countries, but it's not the whole countries, it's just the areas within the countries that are in conflict. So you now have to, public companies now, as of 2021, now have to show that if they're using these materials, that they are getting them from the right areas and using smelters that are from getting their own material from the right areas. So there's a list of countries that you can't get your materials from, and there's actually a white list of smeltering places too. So those are conflict minerals, and there's only 4 of those. Cobalt also comes a lot from the Democratic DRC, but it comes from the south of Congo. So Congo's huge. So the southern area is not as governed by warlords and so much, but there are issues with that. I showed the mineral scutorrhodite. That's the mineral that provides cobalt. It's the only mineral that provides cobalt in large amounts. Usually it's extracted, as I said, as a byproduct of other things. And that comes from Morocco, but that's only 2%. So it's almost negligible. This map here, which shows where cobalt is found around the world, you'll see something that says other lands, and that actually is the ocean. Cobalt is so sought after that they're now considering mining the sea floor for something called manganese nodules. But it's not just manganese. Manganese nodules have nickel, they have cobalt, they have all sorts of things that are really important in them, which is going to be a problem. And that's partly because there's a problem with the cobalt found from the Congo copper belt. This produces huge amounts. And the trouble is, it's really mined artisanally. So, you know, it's quite a lot of child labor and really poor conditions and very hard to monitor. Yeah, you're not meant to, well, I'll just leave it at that, actually. So there's issues with getting cobalt all around the world, and that's one of what we will find out later is a critical metal. So rare earth elements, you probably heard lots about rare earth elements, and maybe you even know that rare earth elements are not so rare. This shows a map of where you can find them around the world, the different kinds of rock types and things. They are found in many places and in many different kinds of minerals, but the thing is, there's just not a lot of them. The other issue with rare earth minerals is that they are very, very similar. It's like trying to figure out which twin is which. Trying to extract the ones them individually takes a lot of chemistry. And this plot here shows, well, the different colors show you the different sources of rocks. Some of them are in sediments, some of them are in igneous rocks, some of them are in muds, and each source of rare earths needs a different kind of chemistry to extract it, to get the different ones. And the plot here, you don't need to look at it in detail, but the yellow areas are like good, low impact extraction processes, whereas the white ones have a huge environmental impact with extracting them. And as you can see, the blue, the top layer here, doesn't have a lot of yellow. I mean, most rare earths come from weathered rocks or intrusives, and there's no great way of extracting the rare earths from them without a significant environmental damage. And it's partly for that reason that the main rare earth supply in the States, as it happens, Mountain Pass, basically stopped producing rare earths by the 2000s. It was also that the process is quite environmentally damaging, and China started, which produced more. You can see on this plot here of the amount by countries. China started to produce a lot, and it started to take the mines and under government control. But with that, they also started to put in quotas. And by 2011, there was a sudden shock. The plot at the top shows the price of rare earth oxides, and all you can see is it was very, very low, and at 2011 it shot up in price. And that's because basically China turned off the supply, and the rest of the world went, oh dear, what do we do now? And you can see what's happened since then. The rest of the world has suddenly taken off and tried to find other sources of rare earths because it suddenly realized how reliant it was on it. And this has led to really all the Western world, started with the States, but followed by the UK, Europe, and then UK and other places, to assess what kind of minerals they need and elements they need and how easy it is to get them. And by that, I don't mean going and digging it up in the ground. I mean the whole process from finding it to processing the different stages, because often it's moved between countries, for one part of it to another, before you get the product that you can finally use. And this plot here shows economic importance. So for every country, it's slightly different. It depends what their industries are or what their, and likewise, their supply risk. For somewhere like Australia, they have most of these things. And so you'll see a plot like this, where there's a whole bunch of minerals and elements in the top right-hand corner, which are now called critical elements. And that happened since 2011. And now there is reviews. Most of the countries are doing regular reviews and updates. And that's true for the UK UK too. The UK has only 31 on their list. The last update was published in March 2023. And compared to the USA, which has about 50 on its list, and Europe that has 43, UK only has 31. Its strategy is slightly different. It's not trying to have national supplies of all these critical elements. It is prospecting for a number of those minerals that you see on the list here: cobalt, copper, things, and lithium. I show here a map of lithium. They're looking in Scotland and Glenbucket area. But it's also just looking at the supply chains and making sure that the economics and the agreements with friendly countries or processors is all in place, and trying to diversify, really, not just to rely on one country. That's had benefits for us. I was involved with, the National Museum of Scotland was involved with a project in Sweden looking at eudialyte and some mines there that were specializing in heavy rare earths. But again, it's this igneous body, and the processing is not very environmentally good, and the project sort of fell through. They were hoping to have make Norra Share, it's called, the first area in Europe that has mined, but that's been put by the wayside. But the point is, we were using eudialytes, which have been in the collection since 170 years ago, way before we ever knew that they might be of use. And it was great that they could be used for such interesting projects. Right, we're getting close to the end. The minerals, if you want to come and see these minerals, I have here a map of our main mineral galleries, which are on the first and the third floor, mostly on the eastern side. I've tried to show it in pink here. They're scattered around. This is one of the reasons why I'm showing you a map. The crystal models that I showed you are on the 5th floor in the technology section. And then the history of geology is in the basement in a place called Beginnings, underneath the modern bit called the Museum of Scotland. So that's a place you'll see a lot of the minerals shown in this talk. And finally, if you can't get to the museum, there is an online resource which just shows you the pictures online, many of these featured here, and that's the link to the page at the bottom. And that, yes, summary for your, I'll set the exam another time and we can see how much you paid attention. But anyway, that's the end of the talk, and thank you for listening.
Oh.